So as I've said probably too many times, it's really, this chapter 7 and chapter 8 are really one big chapter with the point of view of deriving and using examples, working problems, and the conservation of mechanical energy. So we're partway there, and we will derive the conservation of mechanical energy today. We got 3 lectures on this chapter, and that's really the goal today. And we really got to do this one demonstration today, so we'll be doing that at the end, okay? If this is in your way, I'm sorry about that, but we normally do this in the bigger lecture hall, which we call the slant room. You know, those slant rooms, you guys know about, yeah. Where there's an attachment at the ceiling, and then we use this bowling ball, a big bowling ball. You know, there's different sized bowling balls. Do you guys know that? Yeah, this is a big one, heavy. It's very heavy. So, but we just can't do it this quarter. There's a class in there right now. So, okay, so let's get to it. Here's the idea. So, let's consider the simple case where we have a uniform gravitational field, constant gravitational force on a body, and we project it upward with some initial speed v0. We know that it has kinetic energy, right? 1/2 mv0 squared. What's going to happen to that kinetic energy as the object rises here? It's going to get less, right? And in fact, right at the turnaround point here, I've just spread this out, okay? This is really going straight up and straight down, okay? It's not projectile motion, 2-dimensional projectile motion, 1-dimensional motion. Right at the top, what's the kinetic energy? That's exactly right. So then the kinetic energy starts to pick up again, and finally, we're neglecting air resistance here, it's going to be the same as it was before. So the way we think about this is that there's energy. We have this initial energy here. It's kinetic energy. It's being stored as what we call potential energy, and we'll do a rigorous definition in a moment. But this energy here is being stored. More and more of it is being stored in the due to the gravitational field. It's being stored in here gravitationally. Finally, at the top, we hit the max. There's going to be the maximum potential energy, and then we think of it as stored energy because we get it all back on the way back. So the motion here is we start off with kinetic energy, and it goes to 0 at the top, and it's maximum at the beginning and at the end. And in between, the potential energy is a minimum or 0. I'm actually going to revise this and make it a little bit more general, but don't worry about it right now. This is just an idea, right? The potential and the stored energy starts off at a minimum or 0 here, and it increases, and it's a maximum when the object's in the top. When I add these two curves, I get a constant. The total energy is constant. That's the notion. That's the idea. Okay? This potential energy here, or stored energy, is an energy of configuration. Okay? When we change the configuration of the system, we can store energy in it or take energy out. That's where we're headed. Any questions or comments about that? That's the basic idea. So we need a formula. We got to quantify potential energy. How do we do that? Well, if you think of this previous example. The mass has potential energy due to the fact that it's in this gravitational field. And the higher it is, the more gravitational potential energy there is. We can get energy out of that and put it into kinetic energy. So and it also depends upon the mass incidentally. The greater the mass, the greater the potential energy. So here's what we do. This is real physical. We imagine that to get at the potential energy here, we forget our motion right here. Just forget it. Just think of the body and the gravitational field. We define the potential energy to be the work that we have to do to raise the change in potential energy from, let's say, here to here. For right now, we're going to be dealing only with changes in potential energy. We'll remove that later, okay? So the change in potential energy from its minimum value here to a maximum value here is defined to be the work done by an applied force to slowly lift this mass up that distance. We want to do it slowly because this is energy of configuration. We don't want to deal with kinetic energy. That's one reason. Another reason is we know what that applied force has to be. What does the applied force have to be if I very slowly move this up there? What does it have to be? Not zero. The total, yeah, because I'm moving it very slowly, there's some applied force here. It's got to be equal to, because we move it very slowly, infinitely slowly. We move it quasi-statically. So there's essentially no acceleration. Yeah, I know, it would take an infinite amount of time, but you just live with it, okay? So I'm going to very slowly move this. We're really taking a limit here. So I can tell that it's bothering some of you. So we imagine doing this very slowly, right? And you're right, this will be greater than that, okay? But in the limit, as I move it more and more slowly, this is going to get less, this is going to approach that. And yeah, and the limit, when we do it infinitely slowly, it'll be equal to that. So that's our definition of the change in potential energy. It's defined to be to take the system from one configuration to another. In this case, the configuration, if we're thinking about the bottom and the top, we take it from here to here. It's the work that we put into this thing, the work that we have to do, an external agent does, to make that change in the system when it's done very slowly. That's the definition of potential and change in potential energy. Now you'll notice here we have two ways, they're equivalent, two ways of thinking of the change in potential energy. The more physical way, and you can tell by just the way I'm talking about it here, the more physical way is the change in potential energy is the work we have to do to slowly make the change. That's more physical. However, calculationally, when we want to calculate this, it's better to deal with the actual, this is just a slight shift in perspective, it's better to deal with the work done by the force. Because it's moved slowly, the work done by the applied force is equal and opposite to the work done by the force, in this case mg. So they have to be equal and opposite because the forces are equal and opposite. So the works are going to have to be. So we have these two slightly different perspectives that we'll use here. But when you'll notice that when I'm trying to be physical, when we want to be physical about this, this is the physical way. And I think you can probably already tell that, right? And you know where we're headed. I'm on the outside here. I'm putting work. I'm putting energy. Work is energy, as we will see. We've already seen that with the work kinetic energy theorem. We've already got a good indication of that. So I'm doing work on this system. I'm putting energy into the system. And we get an identical change in potential energy. I'm storing energy in the system. And that's the amount. The work that I do is the energy stored in the system. So this is the more physical way, but calculationally we'll be using that. They're the same though. Okay, now, you might think the natural thing here is to start looking at special cases like gravity. Calculate, look at this for gravity. For a spring, we have this nice example of a non-constant force. It's springs, right? Hooke's law. But no, that's not what we can, we've got a bigger issue we've got to take care of here. The problem is we have to qualify this. This is not always true. All right, and there's a very simple example. Friction. So let's look at friction. Now I don't know if you can see, you can see. Maybe this is better. So I've got this eraser, right? So if we believe this, And let's try to apply it to friction. Okay? So I slowly move this eraser along here from one point to another. So I've done work, and if you believe the potential energy, I've increased the potential energy system. Can I get that energy back? Well, yeah, I can get some of it back. Because what's happened? What?
It's not just going to roll back for you.
No, right. So I move this over here, right? I've done work. It's the kinetic frictional force times the normal force, which is mg, and times the distance. That's the work that I've done. Is that energy stored in the system? Can I get it back? Well, it doesn't look like I can get it back at all, right? It turns out, the surfaces here are going to heat up a little bit because of the friction. You know that. So, because the temperature's gone up, I can get some of that energy back. I can get some of it back. Whenever you've got a system that's hotter, you can extract some heat. That's energy. You can turn it into useful work. But we can't get 100% of it back. And that's quantified by what's called the second law of thermodynamics. And it's reasonable, I think. I think you'll buy the fact that we're getting this heating. We can't get all that energy back. It is interesting we can get some of it back, but that's because it's got a little hotter. But we can't get all of it back. So the problem here is that there's no potential energy doesn't exist for friction. And let's see. So how do we know? We're confronted now with a problem. How do we know whether a potential energy exists for a force or not? Well, smart people have thought about this, and here's the answer. It has to do with whether the force is conservative or non-conservative. Every force is either conservative or non-conservative. And we'll discuss this. If it's conservative, a potential energy exists. If it's non-conservative, it doesn't exist. We have to treat it separately. And we'll see how that's done in the third lecture on this. So, what do we mean by conservative force? A force is conservative. When we say it's conservative, it means that the work done by the force on a body, when it's slowly moved, we don't have to actually say slowly, because this is the work done by the force, like gravity or a spring. It's the work done. A force is conservative, said to be conservative, if the work done by the force is independent of the path. So what does that mean? So here we are. This is like X, Y, and Z, right? We start from one point here, and you can imagine this to be. This can be anything. This force here. It could be the gravitational force. It could be the force of a spring. It could be a frictional force. Okay. Whether or not it's conservative depends upon the fact that if you find the work done by this is the work done by the force from this point to that point along some path. It's summing up all the individual works. We've seen this before, right? So if that work is independent of the path, if you get the same answer regardless of which path you take, you could head off straight here, or you could go down here and up here and back, anything. If you always get the same value, then the force is said to be conservative. All right? And we'll show that a potential energy, it's going to be easy to see that potential energy function exists. If it's dependent upon the path, then it's non-conservative. All right, so what about friction? I've got this eraser here. I go from one point to another. So let's look at maybe I better put this on the board. Let's look at the top view here. So here's this eraser on this table, and there's friction here. So suppose I move it here, some distance d here. What's the work that the frictional force has done? Well, first of all, it's opposite direction, and it's going to be the kinetic frictional force, because it's moving, times the normal force, which is mg, times the distance d. That's the work done by the frictional force. What if I move it? What if I move it this way?
More friction.
It's always against the motion. And now I've got mu k mg times this distance plus that distance plus it's more work. Well, it's more negative. Okay? The absolute value is greater. It's not conservative. So I know this seems probably maybe too mathematical for you, but this is really, the people have had hundreds of years. They worked on this for hundreds of years. And this is really the proper way. This is the best way to approach this. The issue of whether or not you can get a potential energy, as we'll see. We haven't gotten it quite there yet. But you want to make sure you understand this because it plays a fundamental role in potential energy, as we'll see. So again, the frictional force, the work done by the frictional force is clearly path dependent. Now there's another way, so it's not conservative. There's another alternative perspective here. We define conservative to be, it's path independent from one point to the next. So that's embodied in this diagram here. The force does the same work when we imagine, moving this body along here or along here. There's another way to look at it. Consider the work done by the force around any closed path. So you start here and you end here. For a conservative force, what's that work going to be? Can you see it? So let's say I go here and I'm just going to do some work, and now I go back here. Like,
I think it's 0.
yeah. So some of you are seeing this, but clearly not all of you. So here's the idea. There's going to be some work involved here. It's going to be the same here. So when I integrate along here, I get some value. This, okay? Now if I integrate back along here, I'm going to get the same magnet. It's going to be the same, except it's going to have an opposite sign because I'm going against the arrow. There's an arrow here. We're flipping our little increment at every step of the way, so it's going to flip the sign. So whatever work I get here, if it's a conservative force, I'm going to get an equal and opposite work here for a conservative force. So another way of expressing this, and this is sometimes useful, and I'll mention one of its uses right now in a moment, but and I think we might use it later. An equivalent way of looking at this is, instead of thinking of conservative as this path independent, you can think, you get the same value no matter which path you take between 2 points. Here, it's always going to be 0, no matter, you start and stop at the same place, but for any path that you choose, you're always going to get 0. It's always, that's an equivalent definition of a conservative force. And it works nicely here. Let me put some. So we start here, we go here, go here, go here, and go back. Is the work done by friction 0? No way. It's always opposite the motion. It's going to be minus mu k mg times the total distance here. Not the displacement 0, but the total distance. You got to add this distance. In here, you got to add this to that, to that, to that. Friction is non-conservative. Any questions so far or comments? So you can see one reason why this is important. We've defined potential energy as the work done by the applied force when you slowly move it, which is minus the work done by the force. If we get different potential energies for different paths, that's trouble. You can tell that's going to be trouble. But it's removed here because the potential energy does not exist for a non-conservative force. And the physics behind that, the physical reasoning behind that is, when in friction, for example, when we do this, we know that we're going to lose energy to microscopic kinetic energy, which is heat, right? So we're kind of looking ahead again, but we've been doing this since the beginning of the previous chapter. We're losing energy here that we can't get back. When at most we can get some of it back, but we cannot get all of it back. So friction, no potential energy associated with friction. We can't store energy in there and get it all back. Now I know this is pretty mathematical here, but what we're doing is we're going to derive this conservation of mechanical energy, and then we're going to see how useful, it's extremely useful in solving problems. Not all problems, as we'll find, but a certain class of problems. When you ask certain questions that don't involve time, as we will see, it can lead quickly to solutions. But it's also, it's conceptually important. And like I've told you, it is probably the single most important fact in physics, because energy is conserved in general, beyond mechanics. We're developing it here for mechanics. Okay, so now we're going to consider specific examples of potential energy. And we're going to start off with a constant gravitational force. Is the force conservative? Excuse me. So we start from one point, go to another point. Hold on. This could be any other point, right? And we ask, is the work done by the gravitational force, is it independent of the path? We've actually already answered this question, haven't we? Let me remind you, here's the work done by gravity where you have to integrate along the path. We write out what mg is choosing up to be positive. G is just going to be the magnitude of G minus J, so that's why I have the minus sign here. We dot it with the displacement. And you can see here, and we did this before, all that's important is the change in height. Because, that's what the math tells us. And physically, we know it's true, because if I'm going to move something from here over to here, it takes no work for me to move it transversely. Because the force that I'm exerting is here. If it's moving slowly, I'm exerting a force here, and the displacement's perpendicular in the x or z directions. Okay, so all that's important is the y, and it's not going to depend upon how I get from here to here, is it? I have to do a certain amount of work to get it to go to there. How much work does it take for me to do this? The same, because it's going to cancel here, isn't it? So I take a certain amount of work to go to here, then I put more work in to bring it up to there, but then I'm going to get all that back when I go here, right? Or I could go down here and up, right? It's only going to depend what the math is telling us here, and it's very physical. It's got to be, just also due to physical reasoning. It only depends upon the change in height, the change in y coordinate. So, because it's path independent, it is conservative, and gravitational potential energy will exist. And it's given by this. It's the work done by an applied force to slowly move the body from one point to another point. And because we're doing it slowly, it's minus the work done by gravity. And we just saw that the work done by gravity is minus mg delta y. So the potential energy here will be the change in potential energy going from one point to another is mg times the change in y coordinate. Now, delta y is positive here, but we could go the other way, right? This could be our initial point. Delta y will be negative. The potential energy in the system has gone down. Okay, and the system has done positive work on us. Now, so far we've dealt with changes in potential energy, right? So It involves two positions because it's a change. That's really inconvenient. We would like to be able to get rid of this delta U and just make it a U. We'd like to be able to talk about a potential energy as a function of just one position. We can do that, and it's actually very easy. It causes students a little trouble in the beginning, and I'll try to prevent that as we talk about it. But here's the idea. All that's physically important are changes in potential energy. That's all that can be. That's all that we've been dealing with so far, and that's all that's going to matter. We've changed the potential energy. So, what that means is we have a freedom here. We can take for gravity. We can take, and as we'll see for springs too, and any other conservative force, we can choose a certain height. We can call that y is equal to 0, right? And you know this. We've seen this before. We can choose our coordinate system anywhere we want to. For example, some of you, when you saw projectile motion problems, you might choose the origin to be where at the ground or something, where something hits, right? But you can also choose the origin to be up. If it's fired off some height, we can choose the origin to be up there. You get the same answer. So what we do here is we have this freedom. We can call our y origin anywhere we want to. That you know. And now the other thing we can do is, because all that's important are changes in potential energy, we can arbitrarily call the potential energy 0 here. See, all that's important is delta U. That's all we're dealing with here is delta U. So we can call the potential energy at this reference location here. We can call it anything we want to. And almost always people take it to be 0. That's the appropriate thing here. If we do that, we get a very simple expression for the potential energy. It's just this. And you can verify this, right? If you take the change here from one y value to another, we just get this. Now, the one thing you have to be, and again, we can do that because all that's important in here is the change in potential energy. But once you set your reference level here in gravity or for any other conservative force, and you're solving a problem, you've got to stick with that. Don't change it halfway through, midway through the problem, right? Because you'll be changing the energy of the system. You'll be, I don't know what's going to happen. You won't be I don't think you'll be conserving energy. So here's an example. What's the gravitational potential energy here, if there's some height here to the table? So we've just seen that it's going to be, if we call the table our reference, which is very natural to do, oh, here it is, it'd be mgh, right? Now suppose I move the table, or equivalently, I go over here, I'm at the same height, I haven't changed the height. Now what's the gravitational potential energy?
Greater.
Yeah, if you switch reference locations, but you don't want to do that when you're solving a problem. You'll violate energy conservation. I don't know what you're going to get. So there's nothing wrong with this, continuing this origin down here. That's fine. Now, if you're more interested in this than this, then you would probably naturally call this your 0 potential energy. But all that's important are changes in potential energy. So you pick a reference level where it's going to be 0 and you just stick with it. And if you find you don't like it, go back to the beginning of the problem and change it, and then do the problem over. All right, we'll see examples of this. Okay. So that's gravitational potential. Now we have the same problem with a spring, and now you can really see why we want to deal with potential energy rather than changes in potential, even though the latter is all that's physically relevant. We don't want to deal with these two positions. Remember the work done by a spring, going from one position to another position? We did this. It's equal to this. We can integrate this, evaluate it. We get this expression right here. This is ugly, right? So what we're going to do here is, so you set, the change in potential energy is going to be minus this. So what we're going to do is, we're going to define the potential, and here it's really obvious what to do. You'd be crazy not to. What are we going to use for the reference here? What are we going to call zero potential energy in the spring? It's a relaxed state. It's very natural to do that. You don't have to, but you get into a lot of trouble if you don't do that. So we're going to call our, oh, there's a slight mistake there. I never noticed that. This one should be a subscript. Don't worry about it. So the natural thing to do here is we'll choose our reference location, x1 here. We'll choose it to be 0. That's going to be the unstretched state, and we'll call that zero potential energy. And this works fine for classical physics. But as we've discussed in the news lately, and it happened again yesterday, this is not true is not true in general. A spring in its relaxed state actually has this potential energy is actually an absolute quantity. It was Einstein that showed that. A potential energy unstretched has an amount of energy, and it's its mass times the square of the speed of light. It's huge compared to our daily lives, right? And that's the idea behind a nuclear bomb, right? And the second one that was ever been used in a war was dropped 70 years ago yesterday, right? Nagasaki. What's happening there is, for an atomic bomb, is that this fission occurs. This uranium or plutonium, whatever they used one case, another one case, and there's the final products. There's been a decrease in mass. The mass has gone down, and that corresponds to an amount of energy equal to that mass times the square of the speed of light. So that's the idea behind. That's the basic idea behind a bomb. You're not conserving mass, which in classical physics we always assume that mass is conserved. We don't worry about it. But there is a potential energy there. It's hard to get at, but if you're clever and you work on it, you can, if you, I was thinking about dissolving a spring in acid. I'll have to think about it. I better not say that. But that's the idea of a nuclear atomic bomb. What's the idea of a hydrogen bomb? Anybody know? That's what's going on in the sun. When you fuse, when you're on the other side, small nuclei, if you fuse hydrogen into helium, again, the final mass is less than the initial mass. So you release energy. That's ultimately how the sun works. It's an involved cycle. But the effect, what's going on there is hydrogen is being fused into helium, and there's a huge amount of energy released. And that's the idea of the 50 megaton Russian, I should say Soviet bomb. It was 50 megatons. Somebody looked it up. Yeah. Okay. So we have this. That's really nice. 1/2 kx squared. That's the energy stored in the spring. Classically, right? Forget the relativistic. It's classically. So when the spring is unstretched, there's no potential. This is very natural. There's no potential energy in there. Also, you'll notice it doesn't depend upon whether x is plus or minus. If I stretch the spring a certain distance, I've stored energy in there. If I compress it the same distance, same energy. It's a symmetric situation. And we explicitly see that here. So we're going to be doing a lot of problems with this, with gravity and springs.
So this assumes that it's a classic spring, right? Where it's not.
Yeah, this is Newtonian mechanics is what we call classical physics. It's not relativistic. It's only an approximation, although it's often an extremely good approximation, and it would be nobody could measure the difference. But remember when speeds get comparable to the speed of light? Remember relative velocity that we talked about that seems so obvious? Like the quiz problem with the train car that a lot of you came by and talked to me about? That's okay. somebody throws something in the train car at, what was it, how many miles per hour?
16.
60, and the train is moving 40, somebody on the ground is going to see 100 miles per hour. That's only an approximation. It's extremely good, but when objects start moving the speed of light, Newtonian physics breaks down. So yes?
I'm not talking about a spring at the speed of light. I'm just talking about a spring that's...
No, it's not just the speed, that's just one example of how classical physics can break down. If you start monkeying around with nuclear reactions, it breaks down. It breaks down. Okay, so now here's the idea. So now we can do conservation of mechanical energy because we've done potential, we've done kinetic energy, we've got the work kinetic energy theorem. The work done by the net force is the change in kinetic energy. It's always true, and from now on it's classical, right? I don't want to keep saying classical or non-relativistic. But this is all the whole course here, except for little pieces of discussion, is classical or non-relativistic. Ultimately, it can break down. But you know, it's good enough to put somebody on the moon. That's what they used to say. I don't know if they still say it or not, but it's fine. It's very accurate. And you might say, wait a minute, what about the rocket fuel? Those are all chemical reactions. There was nothing nuclear going on there. So this dealing with this rest energy, this mc squared, doesn't come into play there. Did not come into play there. So remember, the work done by the net force is the change in kinetic energy. Now we're thinking about a single body here, okay? And just think of one conservative force that's doing the work. There could be other forces, but they don't do any work. We can easily generalize that later. Let's just do the simple case first. A single body, a single force that's doing work, and it's a conservative force. Okay, so you know, it could be gravity, it could be a spring. We could be on an inclined plane, right? But no friction. So there's a normal force, but it doesn't do any work. So we derive this. Remember, we derive this for Newton's second law. So here's what we do. Because the force is conservative, we know there's going to be a potential energy function. And it's the only force that's doing the net, it's doing the net work, doing any net work. So the work done, the change in potential energy will be minus the work done by the force, right? The change in potential energy is the work done by the applied force. Here we want to look at it slightly differently. The work done by the net force is going to be minus the change in potential energy. So I take the kinetic energy here, I replace this with minus delta U. Okay, now here comes the big step. And it looks really obvious, but it's huge. We're going to move this to the other side of the equation. You might say, well, that's trivial. Well, it's really not. It represents a shift in perspective, and we won't fully explain that until the lecture tomorrow. But we're going to move this over here, okay? Now we get this. Anybody have any trouble with that? No, it's obvious, right? But now look what we've got. We're going to define the total energy to be the kinetic energy plus the potential energy. This is then the change in total energy. And we see what is the change in total energy here for this case. It's 0. So this is called, in other words, the mechanical energy is constant, and this is what we mean when we say that energy is conserved. It's constant. And let me point out to you, this is for an isolated system. We've got no, and by that we mean there are no other forces. We just got this one force here. We haven't specified what it is, but we're not throwing in other forces that are doing work, right? That we have to be careful about that. Now, okay, so 10 minutes. Okay, suppose we have two conservative forces. So physicists always do this. We start as simple as we can to make progress. So in our case, we had one conservative force doing the work. There could be other forces, but they don't do any work. That's what we assume. Now suppose we have two conservative forces. Now what's going to happen? Well, as we saw in the problem set, the net work is going to be the sum of the individual works. Because the net force doing the work is the sum of the two forces, the works are going to be the sum of the two works. So, and each work has its own potential energy, right? Potential energy function, because they're both conservative. So the net work will then be the change in total potential energy, and we end up with just what we had before. Okay, now two masses. Now you tell me, what's going to happen with two masses? What's the total kinetic energy? It's going to be the sum of the two kinetic energies, right? So we're going down the same path we went here, essentially. The total kinetic energy has to be the sum, and overall the system there's going to be a work kinetic energy theorem. We know that holds for more than one force. So we end up with the same thing. So this is, I'm going to put a box, I'm going to edit this. This deserves a box, or maybe even a double box. So here's what we've got. For an isolated mechanical system that has only conservative forces, the total mechanical energy is constant. And we have to say isolated here because if there's some influence from the outside, some force from the outside, that can change it. For example, if we've got friction, what's going to happen to the mechanical energy when friction's involved? It's going to get reduced in time, usually. Depends on the situation. Now, I made this sound crazy, bringing this over to the other side, I made this sound really dramatic, even though it's a very simple mathematical step. It does represent a shift in our perspective. We're going to talk about that tomorrow, but right now we got to do the demonstration, okay? So here's the idea. This is this cast iron ball, solid ball that we used for that when we broke the string for the inertia experiment. Remember there was another eyelet here. So this is heavy, okay? If I release it from rest here, what happens from an energy point of view? What's the initial energy? There's no initial kinetic energy. What's the energy?
Potential.
Yeah, now we could actually say that there's negative potential energy here. That's not going to cause a problem because all that's important are changes of potential energy. But let's not worry about that right now, okay? We will actually I think we're actually going to solve some problems two ways to show you that it doesn't matter where you choose your origin, your reference location, as long as you stick with it. Let's call the reference the floor, okay? Let's avoid this right now. So let's say the floor is zero potential energy. So I've got no kinetic energy. The potential energy is mgh, where h is the distance from this to the floor, right? What happens when I release this and it swings out like that? What's happening to the energy here?
Being transferred into kinetic.
Right. We're losing potential energy, and an equal amount at every little step of the way. The energy we've lost, potential energy we've lost, has gone into kinetic energy. At the bottom here, it's approximately all kinetic energy, right? There is, it's not hitting the floor. So there is a little bit of potential energy here, but it doesn't really matter. Well, all that's important are changes. So the change in potential energy is negative here, negative every step of the way, and it's going an equal amount at each step goes into kinetic energy. What happens on the return here, on the other side? Now it's the opposite, right? So now the kinetic energy is being transferred to, what's wrong, Gary? You won't like that?
No.
Okay. So now the energy is being transferred from potential to kinetic. So if I release it from rest at some height here, what height does it have to go to? Neglecting energy losses, what height does it have to go to here? It's got to go to the same height. And when it comes back, what height is it going to go to? Same as originally, right? So I shouldn't have any problems getting a volunteer to come here so that we can demonstrate this.
Oh, absolutely not.
Yeah, you can kind of see maybe you can see what's coming. Come on, well, I'll do it, but I can do it, but it's better, okay. Adam. Okay, sit in the chair. Okay, now what you're going to do is, you're going to hold this right at your nose.
Oh my goodness.
Okay, right at your nose. Yeah, okay. Now you want to, maybe you can, you want to release this carefully and quickly, okay? Because, yeah, he could push it, and I've tried to do that before in class. Everyone picks up on it. It's very hard to do. But what I'm worried about is he's going to let it go like this. What's going to happen? He's going to lose some energy. The system's going to do work on us. So if you go like this, and kind of let it go slowly, that's cheating. We want to release it, so you want to move your hands very quickly. So what's the idea here? What should happen?
It's going to go right to the same place.
Right, so he shouldn't have to flinch. Okay, release it right at your nose, and then don't move.
Close your eyes.
Oh. Okay, and it's even more dramatic with a big bowling ball, right? Okay, so, oh, we have some time. Oh, that's good. Because there's something else we need to discuss. Okay, so does anybody have any comments about that? We're going to do, because this requires extensive setup, we're going to do we're going to do a smaller version of this and then start to vary it. We'll do that right in the beginning tomorrow. Okay, and we'll do some other examples. Questions, comments?
Going off what we've been talking about, so the energy loss is due to the air drag then?
Yeah, oh, thank you. I forgot. If you look at this carefully, I can't do it. I did it like 10 times since I set this up on Saturday. Do you see what height is it going to?
Just a little bit less.
It's a little bit less. Did everybody see that? God. Here, we need some kind of reference here. Okay, here we go. This won't flinch. Yeah, it wasn't much. Okay, but it's a little less. Okay, so where's that energy? We've dissipated. Energy is not completely an isolated system. We've lost some energy. How do we lose it? Damon said one reason, air drag. The air actually heats up a very small amount. But due to the drag, this kind of frictional force there, the drag force, we're going to lose some energy there. And you see at top, that is actually, it actually is not slight. Oh, it seems to be fixed. But there's going to be a little bit of energy loss there. Okay. But it's actually not really, I don't see the loop slipping, so that's good. But what's the other thing somebody said? Okay, now, yeah, but if I think of this as a spring, and it returns, it starts, you can see it kind of wobbles a little bit. If that goes away when it gets back up here, that's just another form of potential energy, and we should get it all back if it returns to initial state. But with this wobble or flexing, what's going to happen? What happens when you flex? There's some internal friction there. You can dissipate energy. So some energy is being dissipated due to the fact of this flexing here. And how much is in the drag? I don't know. How much is where it is. The string is this. What's the string doing? This is cheap kite string. It stretches. There's going to be some energy loss there. Yeah, I mean, it's under tension here. It actually stretches quite a bit. Okay, so finally, I looked at the lab reports. So here's the problem. Usually with lab courses, I have the groups come by and we discuss, they have the preliminary lab report, and we discuss it, and they go back and make changes and then submit it. Well, I thought I could get away with it this time. I was wrong. All right, so I slept on this, or it slept on me, I'm not sure which. Here's what I think we have to do this. okay?
Fancy the labs.
I've gone through a lot of, there's a lot of red ink on your, I'm going to go through them again. You're going to come by and talk to me and then revise them. I really think we have to do this. It's really the right thing to do. There's a big problem here. And it's my fault, I should have done this. We don't have to do this for every experiment, but in the beginning, you just don't know what it's like to do a physics laboratory report. There's just all kinds of fundamental mistakes.
Nope, sure don't.
What?
Nope, sure don't.
So I'm gonna go through them again
It's a good first start.
and make some